All right, so here we're talking about uninhibited growth models and limited growth models. So there are actually two sections in this, in 2.4, different topics that we want to cover. Actually, let's look at the uninhibited one first. The same thing as exponential growth. If you recall, we talk about exponential growth. It looks like this. This is basically y is equal to e to the x in terms of an exponential function. And it passes through this point 0, 1. For the most basic exponential function. Now, if you recall, we did the derivative of exponential function, and that was 2.2. So if we had y is equal to e to the 5x, you guys remember what the derivative of this was? Y prime. 2.2. How do we find the derivative of the exponential function? 5 times e to the 5x. Okay, so the derivative of the exponential function says we keep this, which is e to the 5x, and multiply by the derivative. So here, this is our u times the derivative of u. So this is 5. 5. So this is a big 5, e to the 5x. One more example. Or maybe 2 more examples, who knows? So y is equal to 6 e to the 7x. What will be the derivative of that? 40. And how did you get that t? Just for everyone else.
87 down to the before the e and multiple with 6 and keep
The exponential part?
yeah.
Okay. So this becomes, it's always going to be the same thing, e to the 7x times the derivative of the exponent times 7, or 7 times 6 e to the 7x. E is getting the 42 e to the 7x. You know, if we about y is equal to negative 10 e to the 8x. What do we think about that? Is this any different from the previous problem? Negative 80. So once again, it's negative 10 e to the 8x times 8, right? The derivative of the exponent. So y prime is equal to 8 times negative 10 e to the 8x, which is how t is getting our answer. You'll notice that this original part here is actually the original function. Right? And it was the same thing here. And the previous problem, this was actually the original function. So when we take the derivative of this exponential function, it's going to be the number in the exponent times the original function. I just want you to see that, because if you go over here on the left, this is what I want to get to. If we have a function y is equal to c, some constant, times e to the kx, when we take the derivative of it, dy by dx, it's going to be k times the original function, which is c e to the kx. Just like the two problems we did over here. Right. Now what this rule is saying, since this is, we already know all this to be y, they are rewriting the derivative of just k times the original function, which is y. So it's just a way of writing it. Same thing here on the right side here. If we have the original function as f of x is equal to c e to the kx, when we get the derivative of this, it's going to be k, which is the number k from the exponent, times the original function. But instead of writing the original function, they just write f of x. So they end up with f prime of x is equal to k times f of x. Is everyone clear on that? What we're actually interested in doing is the reverse, going back from here to here. So if they give us either this or this, the derivative, we know that this k is a number in the exponent. I know T was saying it, I think T said it was something kind of weird this morning, earlier. So let's look at a couple of problems from your homework. No, that's great. So I'm going to copy the first problem, number 1. So here we go. So notice, let's define the general form. So the general form is the original equation. So here we have f prime of x, which is what we have down the bottom here, right? Same thing as this, is equal to 5 times the original function. That means this 5 then is our k. So when we write original function, y will be equal to c e, because we don't know what its constant is until they give it to us. And that's all there is to this. We're done. That's the answer they're looking for. They want you to understand this 5 in the bottom here is the exponent, the exponential function. So this is my MATLAB number 1. I'm going to do the next one. Well, I'm going to post it there so you guys can try it for me. All right, what do you think? This is number 2 in my MATLAB. What do you think the general form of the function is? Just in case you want to see the other one. Anyone with an answer for this? So here the general form is always going to be y is equal to c e to the kt. All right, this is a general form. What are we replacing? We're replacing the k with what? What is k equal to?
With the 10?
With a 10. So the answer to this problem is y is equal to c e to the 10t. That's our answer. It's always a general form of the exponential equation. Sometimes they're going to tell us what c is. Indirectly telling us what k is. So k is our 10. So if they give it to you in this form, they're telling us that's k. They told us what c is. All right, let's look at the next problem. Number 3. All right, so here, between 2006 and 2016, the number of applications or patents N grew by about 4.6% per year. That is N prime of t, the number of patents, is equal to 0.046 N of t. All right, couple of questions. This is a 3-part question. Find the function that satisfies the equation. So here's part A. We just kind of made it bigger. All right, so let's work on the function. The general form. What do we think the general form is? Once again, it's y is equal to, in this case, this is y or n of t, which is a function of patents, is equal to c e to the kt. So What is our k in this problem? Anyone?
Mm,
T says 0.046. I recall. And here, when they give us the derivative, the number before the function itself is the k. So we've been saying up here, right? Always comes before the function itself. K comes before the function. So they give us the derivative. Even this problem, this is our k. K comes before the function. K comes before the function here. That's our k. So our k in this problem is 0.046. So we know this is e to the 0.046 times t, because they didn't tell us time it. Time is equal to 0. But we're trying to find a general form first. What is our c? So c is the initial amount. Remember like when we did those compound interest problem last week, I think it was? We had the PERT formula. It's the same thing. If you remember interest, A equal to PERT. So the initial amount, P. So do you see, no, this is just another form of this equation. So here would be 455,000. So our function n of t is equal to 455,000 e to the 0.046 t. This is our first part of our answer. Now part B says, find the number of patents applicants 2020. So what are they giving us now? They tell us this. Well, we know in 2006, E was equal to 0, which is coming from up here. So in 2020, whoops. What is T equal to? 14, excellent. And if we know that T is equal to 14, we can plug it into this unknown and find the number of patents. So we're doing n of 14, since that's a time, that'd be 455,000 times e to the 0.046 times 14. What do we get? Does anyone else agree with T's answer? In case you're not seeing it, in the chat box, it's 86357.31. And if you round it to the nearest whole number, this would be 8666357. So after 14 years, the number of patents application would be 866,357. It's actually the correct answer. All right, how do we find the rate of change in the number of patents application in 2020? Well, they told us originally that the rate of change was actually equal to K times, N of T. They gave us this. So the rate of change, which is this, so N of 14 would be equal to K, and K was 0.046 times N of T, which we just calculated up here, which was 866,357. And you should get 39,852. And this is applications per year because it's a change. All right, do you guys have any questions on that? Is everyone still there?